Hello and welcome back to Calculus 3, section something, 13.4 on triple integrals. So we're going to add another integral. And we are going to say dv, and in that case we'll be computing the volume. But then we can have a triple integral and then a function dv, and that will be computing the fourth dimensional concept called bulk. Yes. So area, right, 2D, so 1D is length, 2D is area, 3D is volume, 4D is bulk. So what would be, so the volume is kind of the surface area of bulk. It's interesting. It gets very interesting later on in higher dimensions. So let's leave it there.
Help us conceptualize that better. Time.
I'm sorry? Yeah.
Oh, okay.
That the object can have density, object can have temperature, right, functions associated, and so on. All right, so now the way to compute the triple integral, let's say it's dx, dy, dz, would be to calculate the most inner integral first.
Is that a partial or that's a
That's an f function, yeah. And then this one, and then this one. So it's the same idea as the double integral, where you compute the most inner integral first. This is fxyz, right, in the middle. So everything that you learned so far with double integrals is going to stay the same. Now we are going to define rectangular integrals and general integrals. So the region is now called D of the function x, y, z dv would be a to b, c to d, e to f of some function, let's say f of x, y, z, and now we go dz, dy, dx. This is known as a rectangular integral because all of the limits are numbers. You can use this integral to compute the volume of the box, of the rectangular box, like your desks or that printer over there, right? Something that doesn't have curved shape to it. So if I want to look at this box, well, this one's calculated in bulk because of the f, but
So the integral is calculated.
yeah, if you take this out, it's a volume, right? Because you have 1, 2, 3 dimensions. dz, dy, dx. Those are the 3 dimensions. But if you put the function in, then that's a 4th dimension. Right? So now I have this box. I want this box to be 5 units in x direction. Let's say it's 3 units in y direction and 2 units in the z direction. So my integral for volume would be no function inside, and I have the most outer integral to be z, x, outer integral is x, so that goes 0 to 5. The inner one is y, 0 to 3, and the z one, that is the all the way in the inside, is 0 to 2. So you integrate inside first. Obviously, these guys take forever to solve and lots of writing because it's the triple integral. We have z calculated from 0 to 2, dy dx. Then that's going to give us double integral of 2, dy dx, 0, 0, 5, and 3. And then we have the integral of 2 in terms of y is going to give us 2y from 0 to 3, which is going to be integral 0 to 5 on 6y. Sorry. Yeah. No, it's just 6. dx, there we go. And finally, we're getting 30. Now, 5 times 3 is 15 times 2 is 30. So next time you're tutoring a kid and they say, but why? There you go. It's a triple integral from there. So this would be the rectangular integral. And clearly, these guys are much harder to set up because now you have 3 dimensions to worry about in a setup. Your domain is 3-dimensional because all of those 3 dimensions go into limits. And then you have a function. So the double integral was easier than this, right? Because double integral, you were looking at just xy plane and figuring stuff out. All right. So now, what is happening with the most general integral? I want to use the same letters, so they're using G and H. Okay, good. So let's take a look at the most general case. All right, so please look at this stuff and then write it later. The outer integral, try to understand it. The outer integral is in terms of x, and we know that's a and b. We know that for all iterated integrals, your outer limits must be numbers so that you get a number at the end. Then we move 1 inside, and this is y integral. Y is a function only of x. So I'm going to have g of x and h of x over here. Now, as you can see, these two actually constitute the double integral general region, right? It's the same. And then, as I move further in, z is a function of both x and a y. So we call that capital G, xy, and capital H, xy. Now, let's talk how to set this up easily. I'm going to label certain things. Well, first off, I have to box this because this is the formula for 13.4. General region. Yeah. What do you mean you didn't do anything?
That's suspicious.
All right. Let's see, guys. This integral here is going to be top and bottom of your shape. When you have a shape like this, and the bottom is a flat surface, that will be your z equals 0. If you lift it higher, it becomes z equals 1. The top could be something rounded, like a parabola. Parabola as z equals 16 minus x squared minus y squared. X squared, y squared, right? So that will be the top. It could be parabola on the bottom, parabola on the top. What do we get there?
What did you say?
So, yeah, you got to figure these things out now. So, that integral there is going to be, the top shape is something, and the bottom shape is something. Maybe the bottom is parabola and the top is flat. So it's going to go from x squared plus y squared on the lower limit to z equals 6 on top, flat, right? So the most inner integral is going to define the top and the bottom of the shape. What type of the 3D object, or what kind of shape you have on top and the bottom. Now, to move inside is your good old 2D region from your 2D integral. So this over here is actually region R from double integrals. So, what are we doing? Well, we are just upgrading and allowing for more freedom in shapes that we can work on. So, if I have a shape, Taco Bell. I've never eaten there, but it's, which is the reason why I'm still alive and in very good health.
We have a different one in DC.
Can you turn off the fan?
All right. Princess is fold over here.
Yeah.
So, guys, I'm going to set up the double integral and the triple integral for this shape. The double integral for this shape, in order for me to compute the volume, we'll have to have a function inside, and the triple integral will go without function inside, because triple integral is already 3 variables. Double integral requires a function in order to bump up to 3 dimensions. Now, looking at the shape, I see that z on top is 6 minus x squared minus y squared, because it's a paraboloid that opens downwards. On the bottom of the shape, I have a flat surface z equals 0 because it rests on the xy plane. To set this up on the double integral, this is 13.2 actually. To set it up on 13.2, oh, I can set it on 13.3 as well. So to set it up on a double integral, I have to first figure out my limits and all of these kind of things, which I will. The clearly thing inside that I am integrating would be this function, minus 0. I'm not going to put that, but minus the bottom, right? And then I'm going to have, let's say, dy dx. Now, the limits for this will be, well, negative root 6 and positive root 6, right? Because I have z equals 0. For z equals 0, when I set those things equal to each other, I get that x squared plus y squared is equal to 6. and then that means that the radius is root 6. So when I draw my domain, all of these are root 6s everywhere. So the x will swipe all the way from negative root 6 to positive root 6 and stop. Now, the inner integral, right, when I draw my representative rectangle, my top is touching the top portion of the circle, which is the square root of 6 minus x squared, and the bottom is touching the negative square root of 6 minus x squared. So this is the way to set up the integral for this shape to calculate volume using 13.2. 13.3, polar coordinates, does much better job. It is 6 minus r squared r dr dt, d theta, sorry. And then your radius is 0 to root 6, and your 0 to 2 pi. And now finally, to set up the 13.4 triple integral to calculate the same thing, we actually have the same, and this is what I want to emphasize. We have the same limits. You have to move the third integral out so you can fit everything. And now we have the z dy dx. So z is going to go from 0 to 6 minus x squared minus y squared. There we go. Now what I need you to see is that the first step of solving this triple integral is going to drop you here. Right? Those of you who have a very good understanding of polar coordinates and stuff will immediately recognize that this integral is much easier to solve this way. 13.2 is much easier to solve in this form. So you see that we don't actually need triple integration to address volume at all. That's why the problem for the egg says use double integrals. Because you are, when you stand that egg up and you have whatever function you come up on the bottom and whatever function you have come up on the top, it's the top function minus the bottom function. So over here you'll have just f minus g in calculation, right? We do not need triple integration at all to compute volume of shapes. But I need to calculate the accumulation of the temperature, accumulation of energy, accumulation of blah, 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 right? Something that extends into the fourth dimension on the 3D object. And that is what the triple integration is necessary for. So the limits of the triple integral are going to define the shape that you are looking at 100%. Right? None of the shape, the physical shape of the object, whatever you're touching, none of that stuff is going to go into the function f. Function f is going to be that fourth thing that you are worrying about, right? And the entire object will be in the limits of the thing. Now, the next lecture, 13.5, is going to address the polar coordinates upgrades to the 3D. Polar coordinates will upgrade into cylindrical, r theta z, and polar coordinates are going to upgrade into spherical, r theta phi. So we are going to learn a completely new set of coordinates, right, for the 3D next class, and then do some. That's tomorrow, obviously. Now, what I want to focus on today is setting up these integrals. That is the challenge. The rest is just a joke of computing. Do you know how to integrate? Because what do you have? 3 nested integrals. That's 3 Calc 1 problems in a row. Right? There should not be an issue for any one of you, right, to integrate. But The issue might be the important part, which is Calc3, and that is set up the integral correctly, looking at the object, at the diagram, or reading the text, right? So the book is talking about the volume of the box. I did that. And then they have this wedge. You know the wedge that you use to block the door, right? It's a triangular wedge that... Why? Hold on. There we go. So you have something like this. Now, this is not a piece of cheese because this over here is a straight cut. It's not round. The cheese was the part of the...
You
The
could,
cylinder.
It's not a cake.
you could cut
It's...
cheese to be that shape.
Yes.
Yeah, sure, but then you cut off the frosting, so no.
Eat it. That's not a problem.
First off, I'm not an amateur. I'm not cutting the cake. I take the cake and I eat it. There's no need for cutting. Each cake is just one sitting with a fork. That's number one. Number two, cakes are usually round, and when you cut out the wedge piece, it's actually curved at the end, just like a cheese. Yes, it's a cylinder. What happened?
The whale cakes are not in the shape of, are not round, they're in the shape of a whale.
He's got a good point.
It's still one sitting. I don't care.
What if I wanted my cake to be a triangle? That's my cake.
There?
Cake cannot be triangle. Triangle is two-dimensional.
Oh.
I'll
Triangular
make a
prism.
1 inch.
I think.
1 inch thickness. Now we're talking about triangular prism, which is what you meant. See,
Well, you said the
I asked you on a day one, all of you, not to try and troll me because I'll go back at you. Retaliate.
You say that like that's not the goal.
So all of the problems that are done in a textbook, please read those because you know all the letters and numbers. I'm going to jump into the homework part and set up one of these shapes since it looks like you guys want to go. Weak. Let's talk about problem 16 because it has a lot of cool features.
Can you also unlock the next homework assignments?
The last one. Well,
What happened?
Can you also unlock the next homework assignment?
Sure, $10. All right.
I don't care that
I
much.
don't like it now. Oh. Tim just like
All right. Focus on this so that we can eventually leave. So what do we have? I'm going to draw a line parallel to x-axis. And then I'm going to go in a triangle into the origin. And then I'm going to have a shape that goes like this. The surface on top is z equals sine of y. The plane on at the edge over here is y equals x.
Is that the bottom or the side?
This is the side, and the bottom is z equals 0. And the point is pi 0. Pi 0. Now, I want to set up the limits of this. Now, clearly, if you are given some kind of function, you will plug that into triple integral and integrate and solve. The goal is to learn how to deal with the region. First, we have a choice of dv. dv has a lot of possibilities. We have dx dy dz, we have dy dx dz, we have dx dz dy, and so on, right? Most of the time, it's sufficient to use dz dy dx. Most of the time, not all of the time. Now that helps because it sets the problem the way I explained it in the main formula. If your dz is the most inner integral, then the most inner integral, right, the one in the middle, is going to give you the floor, in our case, the flat piece of the z equals 0, and then the top piece is z equals sine y. So we have that. Now, what is helpful is to draw the shape of the domain, in our case our triangle, on the xy plane on the side, and see its shape and draw the dx rectangle so that you can do this properly. Observe that it's a pi pi, right? It's a pi pi, and then it goes into y-axis, so it goes this way. So this is pi, this is pi, this is 0, and this is pi pi. Draw dx in there, and from there it should be a joke to write the limits, because you see that your x limits are from 0 to pi, and your y limits, bottom is on x, and the top is on pi. One more time. Sine y, sing? Sure, why not?
It's an open G.
Yeah, it's open G, yeah.
Wait,
Well, Y is just an open
It's a cine.
So,
Well, that's what I'm trying to explain. So when you draw dx, right? When you draw dx, the most left position that dx can take is the lower limit, which is 0. The most right position in x that it can take, which is pi, is there. And then for dy, the bottom one goes on the bottom. Well, that's y equals x. And the top one, which is y equals pi, goes on top.
Why is that one y?
This equation over here is y equals x. And this integral over here is y equals, well, y equals x. And y equals pi. So this is how you deal with these integrals. They are giving you a lot of these exercises to work on in a book. And these are your exam questions. Not to compute the integral for 25 minutes because it's a nested triple integral. The only thing that I care about is you writing the triple integral off of these shapes. Because if you are able to do that, you get to eat. Yeah. If you are not able to do that, well, tough luck. Right? Someone else will. Your competition will. So, yeah. So we'll set up at least 2 more tomorrow to start off the day. Those will not be streamed, but they will be added to the notes. And then we'll move on with the next lecture, which are cylindrical and spherical coordinates. And then go into the next. The quiz is open on Wednesday, you said, right? Yeah. All right.
Test tomorrow. Yeah.